Have you ever wondered how a submarine can sink hundreds of meters below the ocean surface and then rise back up without any visible propellers pushing it upward? The vessel descends into crushing darkness. The hull groans under immense pressure, and a simple question emerges. How does a machine designed to sink prevent itself from sinking forever? What allows it to hover motionless in the middle of the ocean? And dozens of people survive for months in a sealed metal tube with no connection to the surface. In this video, we'll break down that engineering puzzle step by step. At first glance, a submarine seems straightforward. It moves underwater, carries crew and equipment, and eventually surfaces. But in reality, it performs one of the most demanding tasks in all of engineering. It maintains life in an environment where a single failure means catastrophic loss. In the ocean depths, pressure increases by roughly 1 atmosphere for every 10 meters of descent. At 300 meters, the external force equals 30 times atmospheric pressure at sea level. If the structure is not engineered to withstand these forces, the submarine implodes instantly. A submarine prevents this through precise material science, controlled buoyancy, and redundant safety systems. It transforms what should be a death trap into a stable platform capable of operating silently for extended periods. For a long time, it was believed that submarine design depended mainly on building thick steel walls. The thicker the hull, the deeper it could go. And thickness does matter, but only to a point. Beyond a certain depth, adding more steel creates diminishing returns. The weight increases faster than the strength, and the vessel becomes too heavy to surface efficiently. That's why early submarines had shallow operational ceilings despite robust construction. The problem was not just strength, it was understanding how forces distribute across curved surfaces under extreme pressure. To fully solve the depth challenge, you need more than thick metal. You need geometry that redirects stress. The solution is the pressure hull, a cylindrical structure with hemispherical or elliptical end caps. When external pressure is applied to a perfect cylinder, compressive forces distribute evenly around the circumference. This prevents stress concentration at any single point. The shape itself becomes part of the defense. Modern pressure hulls are built from high-yield steel or titanium alloys, carefully welded to eliminate weak seams. Every penetration for hatches, pipes, or sensors is reinforced with heavy frames. The result is a structure that can descend to depths where sunlight never reaches and return intact. The mechanism that allows a submarine to sink or rise is hidden within its ballast system. Along the outer hull are large ballast tanks, open to the sea at the bottom. When the submarine is on the surface, these tanks are filled with air, making the vessel less dense than water. Buoyancy keeps it afloat. To dive, valves at the top open, allowing air to escape while seawater floods in from below. As the tanks fill, the submarine's density increases until it exceeds seawater, and the vessel begins to sink. To surface, compressed air is blown into the ballast tanks, forcing water out and restoring positive buoyancy. This controlled exchange of air and water gives the submarine precise depth control without relying on propulsion alone. But how do you maintain a specific depth once you've reached it? A submarine operating at depth is constantly adjusting for changes in water density, temperature, and load distribution. The trim system handles this. Internal trim tanks located fore and aft can be filled or emptied with small amounts of water to shift the vessel's center of gravity. By transferring water between these tanks, the crew can keep the submarine level even as fuel is consumed or equipment is moved. This fine control is critical. A submarine that cannot maintain neutral buoyancy drifts upward or downward uncontrollably, compromising stealth and safety. One of the most critical challenges in submarine operation is providing breathable air for the crew. On the surface, fresh air is drawn in through snorkels or hatches. But submerged, the vessel is completely sealed. Oxygen is consumed, carbon dioxide accumulates, and without intervention, the atmosphere becomes toxic within hours. That's why life support systems are core survival equipment. Submarines carry oxygen stored in high-pressure tanks or generated through electrolysis of seawater. Carbon dioxide is removed using chemical scrubbers containing lithium hydroxide that absorb the gas. Humidity is controlled, temperature regulated, and air continuously circulated to prevent contamination. The result is an artificial environment that can sustain human life far longer than the vessel's food supplies would suggest. Unlike surface ships, a submarine does not steer by turning a rudder alone. Maneuvering underwater requires control in 3 dimensions. Horizontal rudders, called stern planes and bow planes, adjust the submarine's pitch. When the stern planes angle downward, the rear of the vessel rises, tilting the submarine upward. When they angle upward, the opposite occurs. Combined with forward propulsion, this creates a controlled ascent or descent. Vertical rudders control direction in the horizontal plane, just like a surface ship. But the real skill lies in coordinating all control surfaces simultaneously to achieve smooth, predictable motion. A poorly handled submarine can broach the surface unexpectedly or dive past its safe operating depth in seconds. Propulsion in modern submarines is designed for stealth as much as power. Diesel-electric submarines use electric motors powered by batteries when submerged, producing almost no noise. On the surface or at periscope depth, diesel generators recharge the batteries, but this requires air intake and exhaust, which limits submerged endurance. Nuclear-powered submarines solve this entirely. A nuclear reactor generates heat that produces steam, driving turbines connected to the propeller shaft. This system requires no external air and can operate for years without refueling. The trade-off is complexity. Nuclear reactors demand extensive shielding, trained personnel, and rigorous safety protocols. But the operational freedom they provide makes them preferred for long-duration strategic missions. Operating a submarine is not only a technical challenge, but also a psychological one for the crew. Enclosed spaces, artificial lighting, and the absence of natural day-night cycles create a disorienting environment. Over time, fatigue accumulates, concentration decreases, and the risk of human error increases. Without proper crew rotation and support, even the most advanced submarine can become unsafe. That's why modern submarines emphasize habitability. Bunks are designed for rest. Common areas allow social interaction, and air quality is monitored continuously. As a result, crews can remain effective during deployments lasting several months, maintaining operational readiness without compromising mental health. Despite their similar appearance, there is no such thing as a universal submarine. Each type is designed for a specific mission. Attack submarines are built for speed, maneuverability, and anti-ship warfare. Ballistic missile submarines are large platforms designed to remain undetected while carrying strategic nuclear weapons. Cruise missile submarines focus on land attack capabilities, launching precision strikes from offshore. Research submarines are smaller, optimized for deep-sea exploration and scientific data collection. Choosing the wrong type leads not only to operational failure, but also to unnecessary risk for the crew and vessel. Modern submarines are among the most expensive military assets ever built. Entry-level diesel-electric submarines typically cost between $200 million and $600 million. Nuclear-powered attack submarines usually fall between $1.5 billion and $3 billion, while ballistic missile submarines can exceed $4 billion, depending on payload capacity and stealth technology. High-end models equipped with advanced sonar systems, air-independent propulsion, and long-range missile systems can surpass these figures significantly. The cost reflects not just the vessel itself, but decades of research, testing, and the infrastructure required to support submarine operations. A modern submarine is more than just a vessel that goes underwater. It represents a balance between survival under pressure, stealth in hostile waters, and human endurance in isolation. A good submarine descends to operational depth safely, remains undetected for as long as necessary, and protects the people who crew it every day. If you'd like to learn how other complex machines work, let us know in the comments.